All right, so now we're going to be looking at the derivative as well as differentials and a couple of things having to do with setting up the derivative. So to start with, we have the definition of the average rate of change, which is basically the difference between 2 points in terms of slope. So we start out with taking the vertical component of the slope between 2 points to be f of a plus h minus f of a. And then we divide by the horizontal component of a plus h minus a. This will give us rise over run and can be simplified down to format of f of a plus h minus f of a all over h. So the a's will cancel out with that particular format. And this will be true when h is not equal to 0. So when we have two distinct points which are not equal to each other, we can always take that average rate of change between the two. In the case of looking at instantaneous rate of change, we can take the limit as h approaches 0 of f of a plus h minus f of a over h. And that'll be the instantaneous change at a point of what the slope would roughly be of what sort of the tangent line would kind of be parallel with for a point. And so you can take a look at some sort of the properties at a point by taking that limit as the difference between 2 points approaches 0. That's how we can get around looking at just 1 point or looking at the slope at just 1 point. We can also extrapolate this into a full function, which we can call the derivative, by changing that particular point A to just a general variable x, and then solving for the function as a whole. So we define that as f prime of x equaling the limit of h going to 0 of f of x plus h minus f of x all over h. This means that we can take the functions f of x plus h and f of x, find their difference, and then simplify down until we can take the actual limit of h going to 0 to find the derivative. Now, this whole process could be somewhat cumbersome to go through for certain functions. So we do have a couple of derivative properties which can help us reduce the complexity of some of the problems that we have to deal with regarding derivatives. So if we start out with a function f of x equaling a constant, then the derivative of that function will always equal 0. So anytime you have a constant and you take the derivative of it, it's going to be 0 because there's no slope between the two. It's all constant. It's all equal to 0 in terms of what the derivative would be or what the rate of change would be, whether it's average or instantaneous. And so 0 is the value of the function of the derivative of constant. We also have the function for a power term of f of x equaling x to the n for some integer n. We would roll off the exponent. So we would get n in front with x to the n minus 1. And this can be shown fairly easily if we go through the process for f of x plus h minus f of x all over h as we take the limit of h going to 0. Since the first term, the x to the n term, will get canceled out by the f of x function, and the next largest term is the nx to the n minus 1, which you can find by binomial expansion of the x plus h terms and the x to the nth power term. But that's more for the specifics of how you get it. It's an interesting process, and that's how you would sort of come to that result of the n x to the n minus 1, and then the reduction for getting that result. So We also have the constant multiplier of k times a function u of x. K is a constant, u of x is a function of x. If we do the derivative of this, then we would have, again, k as a function, but we would also have u prime of x, or the derivative of u, which would be multiplied by it. So you can take that constant, you can pull it out of the derivative, and then figure out what the derivative of the rest of the function would be. And that would be the answer for the function as a whole if you were taking the derivative of it. We can also talk about if we were adding two functions or taking the difference of two functions. And we could take the sum of the function's derivatives or the difference of the function's derivatives in order to find the derivative of the function as a whole. So that's called the sum difference property, and it applies for derivatives. And we'll also take a look later on at e to the x, which is the exponential function. This will later on come into handy, but if you take e to the x and you take the derivative of it, you get back e to the x. So it remains the same function after taking the derivative, which is an interesting property in and of itself, but we'll see more about that later on. All right. Here we have some alternate forms of the derivative. Some of them are more useful than others, but we have f prime of x, which is the most common form. It's seen mostly in your chemistry classes, biology classes, or finance. We also have y to the prime, or y prime, which can be used a lot in entry-level physics and classical mechanics. Beyond that, I don't believe it gets used a whole bunch, but there may be some places which I haven't seen it yet, which it does get used a lot. So it's good to know of that notation. There's also df over dx or dy over dx. And this form gets used a lot in differential equations, as well as partial differential equations and higher level physics. So you'll be taking a look in those classes as sort of how things are changing overall, and then trying to figure out how to relate them to other rates of change. And so having that particular form is helpful because you might take the rate of change with regard to x, or you might take it with regard to another potential function and try to set it equal to something different. There's a lot of interesting stuff that can happen with that particular form of the derivative. So something cool to kind of know about. All right, so differentials, which are somewhat similar to the last form of the derivative that I just mentioned there, are defined as dy equals f prime of x dx, or df equals f prime of x dx. And these help kind of determine the amount you would have to change something in order to change another variable of a sort. So an example that I brought up in class was the example of having to change the size of a donut according to how much dough you've increased or how much more dough you've gotten. Another thing could be just the example that I was talking about with the circle, and having a circle with a certain radius, increasing the radius by a certain amount, and then determining how much more the circumference would increase from that radius change. So those are a couple of things, or a couple of ways that differentials can be applied. Whether they're consequential or inconsequential really depends on the material that you're working with, but they're interesting nonetheless. So they also are helpful later on for integration because they help you determine more stuff which has to go into that. And we'll talk more specifically about that, but just be aware that they are used later on for that particular topic. So, all right, that's it for this one. The next stuff that we'll talk about will be profit, revenue, and cost, but that'll be in another video. So, all right.